Good afternoon. Welcome to our session. Today we're going to talk about how do you work with raster using Python, right? Okay, so I'm Noman, Nawajish Noman. I go by Noman, that's easy. My colleague Liz here. We all work for the Spatial Analyst team at Redlands. So before we get started, just let me see how many of you have actually used Spatial Analyst. Anybody? Oh, why are you here? You know everything, right? How many of you have used ArcInfo by any chance? Quite a few. Okay. How many of you have used AML? Two hands. Okay. How many of you have used Grid? ArcInfo Grid, right? Okay, so mostly Spatial Analyst user. That's good because we're going to talk about Spatial Analyst and Python and Raster data. Okay, so let's get started. So the way we're going to talk about it is actually through an example, right? And part of that example, which is a modeling process, we will introduce things that we do with raster in Python, right? So first, we'll talk about how you can actually manage raster with tools, and how you can perform analysis using Map Algebra, right? And we will kind of elaborate some of this as we go through the presentations, right? The first part will talk to you how to access the analytical capability that we have, and then how to write from simple to complex map algebraic expression. Right. Then we'll also talk about how you can actually improve your analytical capability by adding new functionality, right? And how can you do complex functionality using classes? And then from that, we'll go totally on a different tangent a little bit, that if you don't have any tool, how can you write your own analytical solution actually, right? And then we will finish off with talking about how you can do raster analysis using multiple core, multiprocessing, right? So as I said that we will try to do that through an example. So we are going to present somewhat a complex modeling problem. That's what you may think, but it's really, if you break it up, it's not that complex, right? You'll be working with raster, features, and table, and we will be actually writing Python scripts for various reasons, and we'll go through that. Now, when we go through that, you want to learn Python and raster data more than the modeling itself that we are presenting, because the objective of this session is not to teach you modeling, but actually to teach you the functionality in Python and Map Algebra you can use to do that kind of complex modeling. So kind of, we'll go easy on the modeling part, but we'll focus more on the Python part of it, right? So why do you want to write a script? You're here trying to do Python. You have geoprocessing tools you can open and you can do stuff there, or you can build a model. Why do you want to do Python, right? People do it for many reasons. Some people just do it because they can do it. But if we actually look back and think about why we want to do it, we want to do it because we can reuse it, right? It can be dynamic because if some of the things are changing, you can actually define that as a variable and you can rerun it again and again. You don't have to worry about it, right? You can also extend your capabilities, right? Because as I said, we have many tools, but we don't have everything. And you want to write something, you want to do something, and so you can actually build your own tools. And in many cases, it actually performs very well because it's fully optimized in many cases, right? So we will demonstrate that through an Ashbur model, where we will go through different scenario where it's actually moving by flight. That means it's actually flying and going from one place to another, or it's moving by hitchhiking through roads, campsite, mills, population, and other things. And finally, there is another step where it's randomly moving. So we'll try to simulate all these different scenarios in Python so that you can see how a complex model can be broken down into pieces and then solved through series of scripts or Python statements, right? So now I'm kind of going back to the beginning again. To do raster analysis, why do you do raster analysis, and what are the things you do when you do raster analysis? The very first thing, of course, you want to prepare and manage your raster data, right? So you want to display, you want to add something, copy, delete, all this thing. You can mosaic, you can clip. Now, to do all this thing, you will use something called raster object, and we'll talk a lot more about that. Sometimes you will use NumPy. You have apply environment that you can use to do it, right? To perform the analysis itself, you will rely on Spatial Analyst extension to do it. But the way you will do it is not by opening the tool, but you will write Map Algebra. So it's algebraic expression that you're going to write, and you will do analysis in that manner. So what is Map Algebra? Now, pretty much everybody understands algebraic expression. People explain it in a different way, but in simple words, it's a very powerful algebraic expression through which you can actually execute Spatial Analyst tools, right? It has operators, it has functions, and you are performing geographic analysis. So you're writing an expression, Python expression, which is doing geographic analysis, right? They're utilizing the tool in Spatial Analyst. The strength in creating complex expression, you can actually create a very powerful expression in a very short form, right? It is available through Spatial Analyst module, and it's integrated in Python. That's why we're talking in the context of Python, right? Okay. Now, how do you actually access this Map Algebra, right? There are many entry points in our system, right? The first entry point is raster calculator. Even though it's a tool, it's a dialog, but you can write Map algebraic expression there, right? So it's a Spatial Analyst tool. It has easy to use calculator, interface. If somebody use Spatial Analyst extension from 8.0, use raster calculator, same as this one, right? It's a geoprocessing tool, and you can use it standalone. Open up the tool and use it, or you can use it in model builder, right? The objective is to use it either in these two places, not to really call this tool in Python, because in Python you will be writing expression by itself. You don't need raster calculator to write that expression. You can also do this expression in Python window. You bring up Python window and you can do it, and Liz will show some of these things to you. You can also write your standalone script and do fancy programming there, right? In order to do all this thing, the very first thing is you have to import a module. In Python, you have lots of module, packages. So in our ArcPy package, we have a module that is our Spatial Analyst module, right? Like every module, it has to be imported. Now, we don't want you to import in any way you like. In theory, you can do that, but there is an advantage of doing the way we're saying, where you import ArcPy, and from ArcPy import environment, and then from ArcPy.sa import star. Now, if you are a hardcore Python programmer, you will cringe to it. I said, why am I importing everything? Just bear with me. You will see that by importing in this manner, you can write much simpler expression. You don't have to qualify every function you use, and that way your expression become much more simpler. That's why we recommend this way when you're doing map algebraic expression. Now, what is the general syntax for this, right? The general syntax for writing is very simple, right? Your output goes in the left-hand side, and your tool, parameter, and operator all goes in the right-hand side. Simple. Left-hand side is output, right-hand side everything else. If you are familiar with doing geoprocessing tool in Python, that's not the style they use. Those tools, core tools, actually have result object in the left-hand side and everything else, including the output on the right-hand side. So please take note of that, and you'll see that in the example. Just in the following example, we're saying from ArcPy.sa. I don't have a problem. From ArcPy.sa, import star, and then out raster, that's my output, equal to slope and my input. So you see output on the left hand side, input on the right hand side, right? And this expression comprised of input data, operators, tools, and parameter, and finally you have output, right? What are the common inputs for analysis? Rasters, features, number, text. We also have few more things, objects, constant, variables. Now if you look at this expression at the bottom, it has your raster, it has string, it has number. Okay. What are those operators? We all know operators are plus, minus, and all the mathematical operators are operators, right? Now, the same operators exist in Python and in Map Algebra or in Spatial Analyst, right? What is the difference, right? Let's see. Out raster 1 equals to in raster 1 plus in raster 2. What does it say? Anybody? It's adding to raster, right? But if you are doing Python without raster, it's adding to numbers or to variable, or a string, it's something else. So depending on the context, it's doing something different. In Map Algebra, when you are doing Spatial Analyst and you are using the same operator plus, it's actually adding to raster together, right? Now, sometimes it doesn't know that whether you are actually referring to a raster or you are referring to a string because you want to specify the name. So to avoid that confusion, not only confusion, it actually won't work. So what you want to do, you want to actually cast your raster as raster. And you have seen that in other programming, right? If you have an integer, you do int, you have float, you do float. So it's cast. You cast that thing as a raster and then you do your operation. So at the bottom you can see out raster 1 equals to raster, then raster name 1 if it is the name, then plus raster name 2, and you are adding them together. There are other expressions to show you that you can actually add a raster with a number, right? The most important example is at the bottom. You see it is using the output of the second expression and then adding something else to that. This is where the raster object becomes much more powerful, and we'll talk about that a little bit more. Now when you are adding something to a raster object, it is already raster, therefore you don't have to cast it as a raster anymore. So you see the out rast 2, we're not casting it as a raster because it's already a raster, but the raster name 2, we're casting it as a raster because it's just a string. What are the tools we have in Map Algebra tool? What are the Map Algebra tools? So all the Spatial Analyst tools you see in the toolbox are available as your Map Algebra tools in Python in the module, right? You can actually use all of them, right? You can also use any other geoprocessing tool, right? But remember, the tools are case sensitive, right? Now, if you look at it, how does it look, right? In your tool dialog, you have input, output, and other parameter, and when you actually define that in Map Algebra, it's pretty much how the tool is execute, right? It has unique set of parameter, some are required, some are optional, and some are numbers, strings, objects, and when you actually write the expression, you see your output and then slope is the name of the tool, your input, and then the other parameters going there. So pretty much same, you just have to remember to move your output on the left hand side, right? What are the output? The output is a raster object which has methods and properties, and the most important thing is the output is temporary in nature, okay? It's temporary in nature. If you don't save it, it will go away, right? With that, I will hand over to Liz so that she can show you some of these things in action.
Thank you, Thank you, Noman. As Noman mentioned, my demos today are going to have to do with a beetle called the emerald ash borer. And this beetle is extremely invasive. It attacks ash trees and just kills them. And my study area is in Vermont, so that's the red box. And the data that you can see displayed in there is some land use data. Not in this demo, but in my next 3 demos, I'm going to use some campsite data, some lumber mills, an urban area, and some major roads. In this demo, I'm just going to briefly show you the Python window and the raster calculator that Noman was speaking about. So I also have some elevation data. The first thing is, this is the Python window down here at the bottom of my map. I was able to enable it by clicking on this Python button. It's just a normal IDE that executes Python. One thing you should know is that the import statement, import ArcPy, already occurs when you open up the app, but I just want to remind you that all of this is available because we've already imported ArcPy. As Noman mentioned, it's really important for Map Algebra that we overload those operators. In order to do that, we have to say from arcpy.sa import everything. And that will help us overload our operators so we can do Map Algebra. Now that I've done that, I'm going to go ahead and create a raster object. So I'm just going to say elev equals raster. And I'm going to select one of my layers. I'm going to select this Vermont elevation layer. Now I have a raster object called elev that was created on the left-hand side. Now this output is temporary by nature, and it does a lot of really neat things. One of the neat things is that off of the raster object, you can get all kinds of properties. I don't know if any of you have ever used the describe method in Python or the get raster properties geoprocessing tool. You don't need that anymore. If you have a raster object, you can get all of that information right here, which is super awesome. I think it's way easier. And there's just a huge list of them there. You can briefly take a look at them, but go back and reflect on them later. I just want you to know they're there. Cell size, yeah, right there. You know, just really handy and easy to have and very accessible. The other thing that we do when we're doing raster analysis in particular is set some environments up front. So to set the environments in Python, arcpy.env, and I'll set the extent here to my study extent. Noman mentioned that the operators are overloaded, which allows us to combine operators and values along with our rasters. So we'll go ahead and see an example of that now. So my elevation data set right now is in feet, and I want to convert it to meters, which is super easy to do because I already have my raster object, and now I can just multiply that by a conversion factor. Oops. Not that conversion factor, though. So, there we go. So now what I've done is I've created a new raster object, which points to, well, a temporary raster, and it has the units meters. Noman also mentioned that we can access all the Spatial Analyst geoprocessing tools via Map Algebra, such as slope. So if we want to see what that looks like, we can say slope out equals, and oops. You can see I got some helpful IntelliSense there that helps me fill in some things, which is a really nice aspect of the Python window, as well as all the help down below what I'm typing, which is nice. So I know that my first input is a raster, but in this case, I'm going to actually use the raster object I just created. So that's my first input, and that's the only one I actually need. The others are optional. And right now I'm running the slope to generate a slope of my study area. Like Noman said, we don't have to do it in the Python window when we're in the application. There's also a raster calculator tool, and it lives inside the Spatial Analyst toolbox. Inside Map Algebra, inside raster calculator is the tool. And this is where you can enter Python syntax. So I've quickly done what I just did in the Python window in just this tiny little model here. So I have my input elevation data, then I used this raster calculator and applied the conversion factor, and then I just ran the slope tool. Just to give you an idea of that's how it's accessible in the app. So we talked about how to do our import statements. We talked about the raster object. We talked about some properties. We talked about some environments, as well as using an operator and a function. And I'll go ahead and hand it back over to Noman now.
Thank you, Liz. She covered a lot of things very fast, right? But if you actually look at them carefully, these are pretty simple things to do, right? One of the most important things she did is she used raster calculator in model builder, in a model. Now, if you step back for a second and said, oh, wait a second, you have all this plus, minus, all these tools there, right? Why can't I just use one after another and then do it, right? Of course you can. You can bring times and do the multiplication. You can do plus. But think about it. If you're doing A times B plus C times D or something, 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 then suddenly how many tools you have to put together, it becomes really cumbersome. But you can still do it. But if you actually use raster calculator, your expression become much more compact, readable. You can actually look at it and immediately see what's happening. But most importantly, it's actually optimized. I'll come to that in a minute. Okay, so moving on, let's see. Complex expression. So she did simple expression. Now we'll kind of do a little bit more complicated thing where you can actually combine multiple operator or tools together to create your expression and still very readable, right? You can read it. Now you can have an output from that complex expression and then pass it down to another one. Now you don't have to write a super long complex expression, but you can actually do a sizable one and take the output and pass it to the next one. You can logically break it down your workflow and do it this way. It's actually good practice to do so, right? Because then you can debug it easily and you can actually think about it more logically, right? If something goes wrong, you can execute one statement at a time and see where things went wrong. Believe me, things go wrong, right? Okay. Now, more on raster object. Raster object is very critical for map algebra and processing with raster, right? It's a variable pointing to a raster, right? Output from a map algebra expression, that could be a raster object, which of course create a raster. Or you can actually point to an existing data set. The way Liz did, first she created an raster object pointing to the DM she wants to work with and then multiplied that with some numbers and stuff like that. Now the data set that is associated with this raster object or the raster object they're pointing to is actually temporary in nature when it's actually the output of your expression. If it is a data set already exists there, of course it's permanent, it's not temporary. But the one that's getting created, new one, is temporary. You have to call save to save it. Now you can argue and you can say, why do I have to do it? Why is it disappearing? Well, think about it. If you are actually doing a complex model and you are creating bunch of intermediate one, either you delete it, clean up and hang on to your final result, or we can do the job for you. So if we are doing complex modeling, I think we thought that if we do that job for you, it's actually better. It's not going away immediately. It's going to go away when you are done with your session or you're killing that object or something. So if you are adding the output to display, you can still see it. It's not that it's somewhere magically disappearing, right? It's disappearing when you are done with it, right? And series of properties are there. Liz already demonstrated that for you, right? And that's actually a good way because on many occasions you will need to know the number of rows, you may need to know the extent, you may need to know the mean or max value because you have to make the decision. And those are actually dynamic, right? So if you actually can query it and use it in a program, the whole thing becomes much more dynamic, right? I mentioned about optimization, right? Before we talk about optimization, let's talk about local tools like plus. If you are doing plus, it's happening what? A cell is added to another cell. It's a local operation, right? Some of the operation that if you're doing A plus B times C, something like that, think about it. You don't really have to do it one by one. What we can do all this thing in one shot, right? So that's the optimization we do. And because of that, you are not running one thing at a time, you are running everything together in that map algebra expression, things become much more faster for you, right? That's the optimization. When entered into a single expression, all local tools and operator are processed together on a per cell basis, which means we are optimizing the heck out of it, right? Okay. Now we're going to go back to our complex model that we started to introduce, and we will actually show you, Liz will show you how to simulate the movement of this ash borer through hitchhiking. Okay.
Okay, so before I move on to that, Noman mentioned that the raster object on the left-hand side is temporary. So you can see I queried it here, and it's true, it's temporary. I just want to talk really fast about how to save that result. So there's a save method off the raster object. And if I just execute it like this, it'll execute and it will persist on disk. It will save, it'll make it a permanent raster to my Scratch workspace. For those of you who, you should look at the environments about Scratch workspace. If I give it a name, it'll go to my current workspace. It'll write it to my current workspace. Or you have the option of giving it a full path and it'll write to disk with the name you provide at that point. So that's how you use the save method to persist your final result. As Noman said, I'm going to talk now about how the ash borer moves around. And I don't know if any of you guys camp, but sometimes at campgrounds you see signs that say, please do not bring in firewood, do not take the firewood here to another camp. And the reason is sometimes that firewood is full of this invasive species, and it's one of the main reasons of how it moves from place to place throughout an area is it's either on lumber leaving lumber mills or it's in firewood that campers inadvertently, unfortunately, move and continue the infestation of this beetle. So let's go ahead and look at this hitchhiking model. So it hitchhikes when it's on wood and it's being transported, not by flying itself there, right? So I don't know if any of you have done any type of suitability modeling, but the first step in solving this problem is kind of figuring out where can this beetle get from. If it's in a campground, it's more likely to be closer to campgrounds, closer to roads, closer to urban areas, closer to lumber mills. And so we've got to kind of create a surface to help us solve this problem about how likely is it to get to one of those locations. So what's important for something like the campgrounds is the distance to the campground. The closer you are to a campground, the more likely you are to find this beetle because that's how it travels. So what I did was, I know that it's not a linear decay function. It's not as it moves away, it becomes on an equal scale less. It's a nonlinear decay function. So the first thing I did is I took the campgrounds, I calculated a Euclidean distance, and then I found the largest distance within my study area just simply so that I can normalize it. Notice here I used get raster properties because I can't really access the raster directly to get the properties off it. And then in this raster calculator expression is where I normalized the distance, so I divided it by the max to get it from 0 to 1, and then I applied a nonlinear decay function as it moves away from the campgrounds. How likely are you to find it? Really likely next to the campground, much less likely the further you move away from it. And I did this for each of my different inputs to my kind of suitability modeling here. And then I combined all those in a raster calculator, which is another complex expression, which is what we're trying to talk about here. So I summed up all these rasters and multiplied each of them by a weight and then divided by the sum. I'm going to show you all this in a script as well, but sometimes a model's easier for some of you and a script's easier for the rest of you. So just to kind of get a picture of what I'm doing, I thought I'd use this model first. So after I have a raster that represents how likely it is for a bug to hitchhike there, now we need to see how likely is it that it can infest that area, right? Is there actually a tree, is there actually an ash tree at that location? Otherwise it's just going to die, it doesn't have food. So that we need to consider that next. So I took that how likely is it that the beetle ends up there, and I said, okay, if it's greater than 0.5, then it's going to be likely. That's what I'm considering likely. Remember, my scale is 0 to 1. So if it's a higher value, it's likely to end up in that location. So I use con to do that. And then I just did some intermediate steps here of converting it to a polygon and dissolving the polygon. And then I created some random points in the locations I identified as likely. And then I checked to see if there's ash under those points. If there's ash, I'm going to say the bug is now living there. It's infested that location. Then I'm going to loop through and run my model or my script again to see where those bugs then hitchhike to. And that's how we can simulate the hitchhiking movement of the emerald borer beetle. So here it is in a script. The first thing I do is my import statements, as you recall seeing in the Python window. Then I set some environment settings, extremely crucial for all raster analysis. Then I set my parameters. And then I actually get into my loop of actual crunching data and doing some analysis. The first thing I do down here is you can see that I run my Euclidean distance tool with my first input. And now, look, I can get the max data just off of the raster object directly. So after I have that maximum distance, then I'll be able to normalize my data to keep it all on the same scale, because like you can't combine apples and oranges, you know? So we need everything on a scale of 0 to 1 so that we can sum them up in that next raster calculator statement. So down here, you see that expression I had inside a raster calculator. Now it's just directly in Python, right? That's my nonlinear decay function, and I'm multiplying it by a weight. Maybe the location of the campgrounds is more significant than the location of the urban area, for example. When I combine them, I get to weight them in terms of their importantness. Down here, you can see my con expression, where I said if it's greater than, if the likelihood is more than 0.5, then consider it as a location to be infested, highly likely to be infested. And then down here, I took the raster that represents where the actual trees are that could be infested, the susceptibility, and then I combined it to say, okay, well, if the beetle ended up there and there's a lot of ash there, then create a newly infested area. And then I looped through this a few times to have that location grow out. So if I come back here and I turn on, so you can see there's a few spots there already, but my script is running right now. And if I refresh this might take too long. If I refresh it, you'll see in a second more locations where the bug has hitch tagged to will draw on my map, because I'm adding to the existing raster. There they are. And it'll do that for each iteration because I'm growing that out. So in that example, I hope that you take away some of these complex expressions where I put multiple functions together. I used functions as well as operators to do some of this analysis like this. And it's really great because it doesn't write intermediate output. So like there's no output created by this division, and after that's there, then it doesn't create an output when it runs the power function and then create an additional output when you apply the weight. It's kind of like a deferred evaluation where it executes that all at once. So there's way fewer read and writes when you're using these operators in Map Algebra. And that's why it's really great to be able to combine them all together in a complex expression like this, or one of the reasons why. And I'll hand it back over to Noman.
Thank you, Liz. A little bit of complex expression, but it's all good because you will have actually this sample and you can try yourself that how we're actually putting this thing together, doing the looping, doing the complex expression. Now, operators are simple. Some tools are very simple. Some tools are not. Like, for example, neighborhood. Right? If you're doing some kind of neighborhood operation, you may have to specify neighborhood, right? And anybody has used focal statistics by any chance? Anybody? A few people here. So, you do that in a tool dialog, you specify something, but the question is, how do you do that when you are actually in Python? To make your life easier, we have created something we call classes. It sounds difficult, but believe me, it's not really, right? So basically, these are kind of a parameter that we're going to use in your Python expression. It's almost like a small tool by itself, you can think of it, and it has a bunch of parameters. You just have to specify a bunch of parameters, and depending on the classes, the number of parameters varies, right? And also depending on the type, the parameter could vary, right? So you'll see that example of that. What is the benefit? The benefit is very flexible because you can easily specify the parameter. That part is flexible. The most important flexibility comes from the fact that you can query it. Because if you run a GP tool, you go away, and suddenly did I use 5 or 7, right? Oh, what happened? If I use 5, can I try with 7? Then you have to open the tool, do it again. But if you're writing script, you can do that very easily. You say, specify 5 and say, what did I do? Oh, 5. Let me add 2 more, 7 now. Let me add 2 more, 9 now. So you can do a lot of what if scenario and modeling using these classes very easily, right? You can create it like that. It's a neighborhood class, neighborhood circle, and of course it requires your radius and the units. You give that, and you can actually now request it back. You are querying it, and then you are changing the argument and actually increasing the radius by 2. Simple, right? Another thing about complex expression, that when you are actually doing raster analysis, sometimes you also have to incorporate feature in your operation. You may want to create a surface first and do raster operation. So you can actually combine all those tools together. Here's an example where you can actually use IDW to bring in feature data and then take the output and actually do raster operation. You can bring in any geoprocessing tool you want in your expression, right? So we're going to go back and show some of this complex nature through another example. Is will show you the movement by flight, where she will use classes and show you some other example.
Okay, so we talked about how the emerald ash beetle can move on logs and firewood and stuff like that, but they fly too. They have wings, right? So that's not their only source of movement. Now, there's some things we need to consider. I know, for example, outside of my study area to the south, all those ash trees are gone. So I know that these beetles are only moving north. So I need to be able to control the direction that they're moving. Not only that, I know that they don't move at all in the winter. You know, you never see beetles flying around in Vermont in the snow, right? So like, how far do they move in the spring? How far do they move in the summer? And how far do they move in the fall? I want to be able to change those and model those things. So this is the idea. Again, I'll show you in the model first. I have known locations of ash borers, are those yellow dots. And then I use the focal statistics tool to control not only the direction, but the distance of where they could possibly move from their known location. And what I did is I specified what's called a wedge neighborhood. And in this case, I sort of set it up to look more like a semicircle than a wedge, because I said from 180 to 0 is kind of the direction they can move, which of course would be north, because it's everything in between. And then I said the radius is cell size of 20. That's how far they can go, the way I have the tool set up here. And then after I see where they can go, then what I do is I see, are there any ash trees there? And if there are ash trees, then infest those ash trees. And then I take that answer and I concatenate it or add it back on to the rest of my infested areas and rerun that model. And I can loop through and I can see how it moves through flight and where the infestation goes in a season or in a year. So let's go ahead and look at the script here. So again, I start with my import statements, my environments, and my variables. Here you can see that I set 3 different distances. I have a 5 to represent 5 cell size for the spring. In the summer they go much further. I say they can go a distance of 20 cells. And in the fall I say they can go 10 cells. I'm not a biologist. This is made up to teach some map algebra. So if somebody knows more about beetles, I'll hand it over and direct all those questions towards you. But that's how far I'm saying that they can move in each season. And then I go ahead and I start my geoprocessing loop kind of down here where the real work gets done. And you can see here this neighborhood wedge. That's the class. Maybe I'm going to back up 1 second. This may help. If I come down here to the Python window and I say A equals focal statistics. So this is the tool, right, that I'm running. It's just in Python. The first input is a raster. I'm just going to kind of cursor through that. And now you can see the next one is the neighborhood. And if I go down and select weight, it's a class that has inputs. And the inputs to this class are the radius, the start angle, and the end angle. And because we've made them classes and not just complex strings, they're extremely easy to iterate through and set different numbers into each loop that I loop through them. And that's what I'm trying to demonstrate in this script. So here I've created this neighborhood wedge, and the distance I'm getting, each time I go through my loop, I'm setting it as a different value, either a 5, a 20, or a 10, to see how far it goes each loop. And again, this is how I'm creating the movement only to the north. And then I run the focal stats tool. After that, I use a complex expression where I take that result and the susceptibility raster, which is the location of the actual trees, and I figure out whether or not they can inhabit that location. So when I run this script, this is what it looks like. So, not a cartographer either. So this is where it starts. They're pixels, not points, so they're hard to see. But that's where they got to in the spring, so relatively short distance. But then in the summer, they could go much further. And you can see there's a contrast between this one and this one. And I'm guessing there's a lot more, well, I know there's a lot more ash in this area where there's no ash here. So they didn't sustain themselves there. And then in the fall, they were able to go a bit further, but not as far as they could travel in the summer. So that's one example of how I used a class to iterate through my loop and set different values very easily and accessibly in Map Algebra. Thank you, Noman.
Thank you, Liz. See, the beauty of this demo was that she used classes to simulate a very complex scenario, different season, distance, and all this thing, and iterate through it with few lines of code, right? Okay, now we're going to switch gear and totally go into a different kind of different side of the Python. Any of you have heard of something called NumPy, NumPy, whatever? Okay, good. Okay, what is the most common thing between a NumPy array and raster? Anybody? Anybody? Yeah? Go ahead.
NumPy actually can break an image into different arrays, so it can get the image values.
Right.
Raster just the image set. So NumPy can also be used to analyze some level images.
Okay, thank you. So, he kind of explained, what is the raster and NumPy array. The most common thing that occurs to me is they're all a bunch of cells with numbers, right? So if you can look at it, raster with all this color, you change that to number, that becomes array. That's an NumPy array, right? Basically, and if you can transform that array, you can work on with them, right? So to make that work easier for you, what we have done some work. So we have first incorporated NumPy with Python. So you install, you can get NumPy. You can use this NumPy to create custom functions, right? And custom tool. There's something that we don't do ourselves. We have not shipped to you, but you want to simulate something. You want to do a different calculation. It comes with a lot of additional functionality: clustering, filtering, linear algebra, optimization, Fourier transformation, morphology, name it. Now, how does it work really in our domain? Basically, we give you very simple two functions, right? One is to create a NumPy array from raster. It's called raster to NumPy array. Simple. That means I'm taking a raster, turning into a NumPy array. The moment it's a NumPy array, there you go. You can have access to those numbers and you play with it, you do whatever you want. You don't like the slope we provide, you compute your own slope. Right? That's the idea. Now once you're done manipulating this number, creating your own fancy slope or a very complex operation, you have this number stored in NumPy array, you want to bring it back to a raster so that you can do other operation to it. So how do you do that? You call NumPy array to raster. Now in the first one you see the input is raster, in raster, and all the other things are optional. When you see all those curly braces, that means parameters are optional. Basically, if your raster becomes too big, you cannot put it in one array, you can just specify your starting point and you can just chop it off, right? That's why those options are there, but you don't have to use it. If your raster is manageable and you can load into the memory, it's fine. On the other side, when you go from NumPy array to raster, your input is of course an array, and then again all the other things are optional, right? So once you do that, you can do your operation and you can do some fancy stuff, and Liz will show you how to do a fancy stuff here.
Okay, I obviously don't have a geoprocessing model of this because NumPy array, it's hard to see in that format. So I'm just going to go ahead and show you the script. Here you can see my import statements, and this is going to be super neat. I import another module this time, one called random. And I'm going to use that because what I want to do, I guess I should start with that, is calculate some random movement for this beetle. So either not hitchhiking and not flying, but sometimes the models and algorithms I have developed in my other two models, the biologists are happy with them, but they say, well, sometimes they end up other places through other ways. And we want to account for some of that random, or how does that random affect the outcome of your model to kind of test its limits. So sometimes you need to introduce something like random into your modeling. And how do you do that? Well, we don't have a tool for it in the geoprocessing tools and Spatial Analyst to do that. But if there's something you want to do and it exists in Python, you can turn it into an array and then access that module. So what I did was I imported the normal stuff as well as random. Then I set my environment settings as I always do, and I define my variables as I always do. And then down here is where it gets really fun. This is what Noman was just talking about. I use the geoprocessing function, the raster to NumPy array, and as input, I put my existing locations of infestation as well as my susceptibility raster, meaning are there trees there? If the bug lands there, will it become infested? So very similar to my other models, it's just a different technique to get some randomness into it. The next, after creating those arrays, how do I use those arrays? Well, I created a function up here where I found a subset of my array, and then I wanted to generate a random movement distance, and that's how I use the random function. Down here you can see off the random module, I use this exponential variate. So the point is I'm using something outside of ArcGIS, outside of Esri, outside of Pro, outside of everything we've done. I'm grabbing a Python module and integrating it into my analysis because someone's already written it, someone's already come up with it, and it's something I need to do that doesn't exist in what we provide to you. And one way to access that is through the NumPy array, and then I can access this random module and apply this to it, and it will return up to a max distance, a random location of where the emerald ash borer could end up. And then I find out if that new location is susceptible to infestation. If it is, I add it to the current infestation, and I can loop through adding these random locations. So if I do it once, it's there, and then another time, just a random point within a certain random distance shows up, and then likewise, the third loop through, more points show up. So the real point is you run raster to NumPy to get your NumPy arrays, and then when you're done doing your analysis, you just turn that back into a raster by using the NumPy array to raster function to export that array back into a raster that you can continue on to use in your geoprocessing modeling and project.
Thank you, Liz. Easy, right? Well, maybe not, but you get the point that you don't have to be limited by the tool we provide to do a complex modeling. You can start with very simple, and you can actually go all the way to very complex. And the good part about Python is not only NumPy, you can actually import many packages. How many packages are out there, I cannot even tell. And you can do a lot of fancy advanced analysis with it. So our framework actually lets you do that, and you can actually turn into a geoprocessing tool, and they all work together. Right? That's the power. Now, I'm switching gear and actually want to talk about something different. I will just introduce the subject here, and at 4 o'clock in Musket B, there is a full session going on. They will talk more in detail how to do multiprocessing, use multicore, and do multiprocessing using Python for vector and raster. So if you're interested, you can go there. But I'm going to introduce some of the core concept that you need to understand if you're trying to do this with rasters, because we're talking rasters here. Now, step back and think about some of the function that we have run. We talk about plus or multiply, those kind of function. Those are local function operating on a cell, right? Then we have talked about focal statistics. That's a focal function that to operate on one cell, I have to look at my neighborhood, right? That's called focal function. There are other functions like zonal function. Anybody has used zonal statistics? Okay, so that's a zonal function. That means you are operating on your entire zone, right? And then global function is something that in order to compute something, we have to look at the entire raster. Those are global function like watershed, distance, those are global function. Now, multiprocessing is actually easy, very, very easy when you are doing local processing. Then focal, Go to zonal is doable, global, very difficult, right? But the fact that a lot of operation you do are in nature of local and focal, sometimes zonal, those are actually very easy to do, right? Here is an example. He says pleasingly parallel problems. Sometimes we say embarrassingly parallel problem, right? That we can do, but we don't do, and we should be doing. Actually, in ArcGIS now, a lot of tools use multiple processor, right? Zonal stat does. We are going through it, and we are doing a lot of them. You have heard about raster analysis, ArcGIS image server running on cloud, parallelized, right? We are doing distributed cluster. So this is the area we are going. Why? Because if you look at your data set, it's not small anymore, right? Those days of where 90-meter data or even 500, those days are gone. Now we're talking about sub-meter level, right? So the resolution of data is really high. Even though if you're not processing big area, you are actually processing significant amount of cells, right? So here is an example. If you want to process that entire raster in one shot, you can do that. It will chunk through it, use one processor. But if you chop it up into 4 pieces, you're doing times or exponent or something, a square root in this example. You can chop it up into 4 pieces and send all 4 pieces to 4 processor and then bring it back, done, right? So these are very easy to do if it is a local function, right? Here is an example what happens to your time. So look at this first one. It says 1 there, and on the y-axis is the time. So if you are using your single processor, the time is, depending on the which function you are running, is like 400 plus or 450 seconds. The moment you divide into 2 pieces, it comes down to 250 seconds. Boom, almost half. You send it to 3 processor, suddenly it's below 200. You send it to 4 processor, it's 150. You see how drastically the time is actually changing? But then it's flattened out. What's really happening? So the reason, somebody might say, why don't I get more performance out of it? Because there is a cost here. The cost is chopping it up, queuing it, sending it to your processor, working, bringing it back. So if you look at your workflow, you have to do certain things here, right? And when you have to chop it up more, you are doing some kind of pre-processing. Those are overhead. Putting them back, overhead. So at one point, the benefit you get out of execution is diminished by the overhead that you are doing. So that's why it's going down and then leveling off. 4 is a good number depending on the type of operation you are doing. So we did this a simple example for a local function and a focal function. It shows that 4 is probably a cutoff line beyond which you are not going to get any benefit out of it. It's a good example to look at. Here is an example, code example here, that somewhere in the middle you can see it's append, and then somewhere it says spool, and then it's sending it and then bring it back. Only 2 statements does all the magic, right? So if you want to actually see how to create a simple execution task and hand it off to pool to do multiple processor, you can go to actually that session at 4 o'clock, Musket B, and you will learn a lot about it. Believe me, it could really change how you actually operate and how your work is done, how fast it is done. Especially if you are familiar with Mosaic, think about it. If you have a large raster that you want to process, chop, and there are tools and they will demonstrate that you can send and say, okay, process this extent, and create all this bunch of output. And then you don't even have to put them back together physically. You can use Mosaic, which will do that dynamically for you. So the workflow becomes much more simpler and efficient, and you can get a lot out of it. Okay? With that, I'm going to summarize what we discussed here. When your problem becomes simple or complex, especially more complex, you need the capability provided by Map Algebra. Your life becomes much easier, right? Map Algebra is powerful, flexible, easy to use, and integrated into Python. right? This is for the people who did map algebra outside of Python in their some other life, right? Access through raster calculator, Python window model builder, right? And scripting. We have talked about raster object, your best friend, and classes, right? Raster object, if you work with raster, raster object is your best friend. You can actually create models that can capture interactions of phenomena, right? And a complex interaction, right? You can also use multiprocessing to improve your performance where applicable. Where applicable is important because you don't want to try to do global function using multiprocessor, not going to work. Focal, you have to be careful because of the overlapping area. I did not mention that. They will mention a little bit, but you know that focal has, when you are actually doing the edges, there is some overlap needs to happen and how to manage that. So there is a little bit trick to it, but still very, very beneficial. And with that, all these demos and everything will be available over there. You will get that slide, so you can try and have fun. With that, thank you very much. We'll take some questions now. Any question?
I have a question.
Sure.
This demos you only you have all the rasters on your local drive, right? Is that possible to do map algebras between local raster and the one on the service, map service? You can have it publish your raster service and do that.
So the question, you want me to take it? Okay. The question is, I'll actually paraphrase. In this example, all the rasters are on local disk. The gentleman is asking that can you run operation where your raster is on disk, but your raster is as a service. In particular, in our case, it's image service, right? That has pixel. Map service doesn't have pixel, right? Image service. The answer to that is yes. All Spatial Analyst tools and in Map Algebra, Python, it takes raster in any form or shape, whether it's a data set on disk or as a service. Okay?
So,
Just a second. I think there's another gentleman had another question, right?
What would be the best practice for summing a long list of rasters? Because I have tried this a number of times. Sometimes it would break rasters.
So if I understand the question is, what is the best way to sum long list of rasters? So you have multiple rasters and you want to sum them up, right? Did you try cell statistics? There is a tool that called cell statistics. You don't have to do A plus B plus C plus D plus E plus F like that. You can actually bring up the cell statistics tool and send everything into it and say, give me the sum. Done. Well, if you have 1,000 and for some reason cell statistics does not take 1,000, I don't know that it won't. It probably will work very fine. If it doesn't, then what do? You do 500, 500, 500, then add them up again. You're doing only sum, right? So you can do first 500 sum, second 500 sum. So cell statistics 4 times, then 1 times, you're done, right? So you just can nest it a little bit and then it will work, right? If not, come by, I'll show you. Yes, ma'am.
I'm sorry, but your statement about using an image service, then it would be, if the image service was a worldwide DEM, so to speak, then it would be key to set my environment at the beginning of my script to just work on the environment in my study area, if you will. Is that
Excellent question and comment, right? So most of the image surveys that you access are probably huge in extent and it has different resolution and whatnot. So the trick is you specify your extent correctly, you specify the cell size you want to work on, right? And that way you can actually control. It's not about that whether tool will fail, there is other limit to it because the server on the other side has a limit how much pixel it's willing to give out, right? So you cannot really get all the pixels you want. It has a limit. So if you try to access that, the server will refuse to give, so you're running operation, you will not get any data, right? So because of all this limitation, it's important to set the extent and cell size, so the number of cells, number of pixels you are actually pulling through server is actually allowed by your server, and then you can chop through it.
In this example, you're setting your extent to actually feature class.
Yeah.
Yep, you can do that. You can set it to a raster, or you can use the numbers that represent the x min, y min, or x max, y max.
Depending on, but it would have to know the projection of something.
That's okay.
It wouldn't
So
matter. They would just know. It would figure it out.
it will figure out. So the questions that you are actually making some really good point. Can I set, when we are doing raster analysis, can I set extent from a feature? The answer is you can set extent from any geodata set, right? You know, whether feature, raster, doesn't matter. It can be of any projection. We will resolve it for you. We'll figure it out, right? We'll do the on-the-fly projection and all this thing. But let's be aware of a couple of things, right? When you are trying to mix things up, cell size, projection, you are actually inherently triggering resampling. So when you are changing cell size, you are triggering resampling. When you are actually doing an extent which is not lining up with your cell, it's moving this way, that way a little bit, you are triggering resampling. So what I recommend is, actually strongly we all recommend, set your extent, set your cell size, set your best friend, snap raster. That's your best friend, snap raster. How many times people have said, I have done this operation, result doesn't look right. What happened? What happened is it happened resampling on the fly, you did not notice, so your value is now falling on the other value that you did not intend, now you are getting wrong result, right? Yes. Sure, no.
I don't understand though, if your cell size is different than your snap raster, what happens?
Okay. So just to demystify first, snap raster has nothing to do with the cell size itself. The snap raster, you can think of it as an infinitely large mesh grid, and you are processing a raster. Only thing we're trying to will match at that point is your left and bottom boundary and line up with that infinitely large mesh. Your snap raster is, think of it as an infinitely large mesh, and the area you are processing will move it slightly so that it kind of align with your left and the bottom. Once that one is fixed, then you can have the same cell size, different cell size, doesn't matter. We'll chop, and then we'll do the work,
But you
right?
can set your cell size as the cell size of a raster.
Of course.
Capture raster and
Of
then
course.
set cell size.
And you can do it for your snap raster. Usually, the way I do it, wherever you are doing a project, you have a raster, that's your primary raster that you are going off of, right? And it could be elevation, land use, something. That is your primary raster, everything else is revolving around that. I usually use that as my cell size and my snap raster, and then everything else builds on top of that, right? Okay? Good questions, comments, thank you. Anything else? Okay, thank you for coming after lunch. It was great, thank you.